Okay, so as I was saying, so all we're gonna do here is we're gonna open up the Y editor. And we're just gonna isolate the Y in each equation into the Y editor. Have we done this before? We talked about this, we haven't? Maybe, maybe not. Okay, so there's two ways we can do this. You can use the fraction editor, but I think it's just more of a hassle, the fraction template, than than it's worth, honestly. What would the steps be? Let's just take this first equation for a second and just look algebraically at there's simple steps. There's always going to be no more than 2 steps to getting the Y by itself. Oops, that's a bad color. If I start off with negative 2x minus 2y equals negative 20, and I want to isolate the y, what do I do?
Just add 2x.
Okay, step 1 is going to be I'm going to add 2x to get rid of that, and then divide the whole thing by negative 2 to get rid of that, to isolate the y, right? Okay, so what would that look like into the calculator? We can use the fraction template, but like I say, I think it's more hassle than it's worth. And I think I've noticed one problem with that. If you use the fraction editor when you're doing this, a lot of times you'll get fractions back in your solutions, which sometimes you don't want. Like for example, in these problems, I'm just asking you to round to the nearest hundredth, and so it's actually a little bit inconvenient. So all you have to do instead is just always, if I wanted to enter this into the calculator without a fraction template, what would it look like?
10.
Okay, but I can't, well, okay, but let's not do any simplifying. If I just wanted to enter that expression,
Negative 2x plus negative 20x.
Negative 20 plus 2x in parentheses.
okay, good, in parentheses, I'd have to open a quantity, negative 20 plus 2x, and then close the quantity. What is that quantity really enclosing? Of this fraction? Yeah, the numerator, right? It's always, when I end up isolating y in one of these linear equations, the set of parentheses is always really just going to end up being the numerator of the fraction you get, right? And then the denominator is just going to be the single number on the bottom, which ended up being the coefficient of x, right? So all we have to ever do is the same steps. And you don't need to simplify. In fact, I would urge you not to, because if you try to simplify, as smart as all you guys are, everybody can make a mistake, and it's just one extra opportunity to make a mistake. The calculator does not require it to be simplified. So just always open a set of parentheses. You're going to start off with whatever's already on the other side opposite the y. So it's a negative 20. We're going to add, in this case, add the 2x to the right side. Close the parentheses and divide by the coefficient of y. That's it. Okay, what are we going to get then for the second one? Yeah, and I'm just going to go ahead just to get in the pattern. This is unnecessary this time. Actually, no, it's not. It is necessary because I've got a 4 times an x. So I still need that in parentheses, don't I? As long as there's more than one thing, and that's 2 factors, a 4 and an x. So I've got my 4x divided by 2, right? And then all I've got to do now is find the solution, right? Okay, so let's talk about that for just a second. How would we go about graphically finding the solution? Where should I probably start? Graph. If I just hit graph, I'm at the mercy of whatever my graph was last set at. So maybe zoom 0. Once again, I'm kind of at the mercy of whatever my last window was, because zoom 0 takes whatever you've chosen the x settings to be, or whatever they currently are, and it's going to choose the appropriate y settings. So I could see people saying maybe zoom standard, and that's okay to do, I think, because it's so easy to do, and I might get lucky, and in this case I did, and I saw the intersection. But what would happen if I didn't see the intersection? Got to make it bigger, right? Because I'd be missing it somehow. The lines would have just been crossing in a place that I didn't see on the window. Now the nice thing about lines is, well, you tell me, do they change based on the scale of the window? No, lines are just always straight, and they're infinite, right? It doesn't matter how big I make the window, the lines are always going to look like lines, right? And so if it doesn't work immediately on zoom 6, I would just go to the window and make the window really big. Like I could go from, if I wanted to, I could go from negative 1,000 to positive 1,000 for my x's. And now I would choose zoom 0, right? Because now I'm going to let the calculator choose whatever y settings I need so I can see both lines on that x scale. Does that make sense? So if I hit zoom 0, doesn't look that different, does it? Even though now I'm going from negative 1,000 to positive 1,000 on the x-axis, or on x-axis, right? Either way, it doesn't make any difference. I just have to be able to see the intersection. And if I can see the intersection, all I have to do is go second calc intersect. And then because they're lines, I don't even have, I can just hit enter 3 times. Once for the first curve, once for the second curve, and once for the guess. It doesn't matter if my guess is way off because there's only one solution for the calculator to find, right? So it'll always find it even if I give it a terrible guess. So just second calc 5 triple enter and it gives me the intersection. Okay? That make sense? Okay, let's do another one. So then this gives us what, 3.33 rounded to 2 places, 6.67. Okay. How about that one? Just try one real quick.
It'll just be infinitely many.
Yeah, it's going to be in there.
No, I just got here and I got that.
So it's going to be, what we're going to do, open a set of parentheses, 57 minus 15x, close quantity, divide by 15. Oops, made a mistake. Open a set of parentheses, 19 minus 5x divided by 5. And if I hit graph, what happens? Same line. Even if I put it on a smaller scale, it still just looks like the same line, doesn't it? Right? Okay, so it's easy to see here because with the color addition, the lines are different colors. But if you don't have the color addition, you're not going to see that because they're both going to be black, right?
Desmos.
So Desmos, right, Desmos will be helpful too. If you're using a regular TI-84 though, what's going to be your trick? How could you tell if they were the same line? It's a pretty easy way to do it. Yeah, turn each line on and off. Turn them off one at a time and see if it changes, right? You know how to turn them on and off, you just go to y equals, and if you unhighlight the equal sign, it turns that line off. So if unhighlighting those lines one at a time has no effect, then they must be the same line, right? Okay? Okay, how about that one? And you guys can probably already see what's happening here with these, but let's try this one. Oops. So the first one, I'm just going to get the quantity 8x divided by negative 8. The second one, I just get, it's already solved for y, so just negative x plus 10. Okay, what do they appear to be? But do I know that they're parallel? I don't know for sure. What are my strategies here? How could I find out using the technology if they're parallel?
Just intersect it, but there's no solution.
Okay, but it's a good idea. But the intersection, if you can't see the intersection on the screen, the calculator is going to tell you it's an error anyway, right? And so I guess one strategy might be to just make the window really big. That's a possibility. There's an easier one though. You can just do this. You could just go second calc, and then if you look down the line at all the different options we have, number 6, that's our fancy calculus way of saying slope, dy dx, called a derivative, and it stands for slope. So if we choose number 6, and then right now it's on line y1, and I hit enter, it tells me that the slope is -1. Okay, if I go, then I have to repeat the process. If I go second, calc, 6, and I hit the down or the up arrow to get up to the other line and hit enter, it tells me the slope is -1. And so that verifies for me that the lines are parallel. Okay, make sense? All right. Okay, so there's one kind of cool little technological shortcut, and that is a really quick and easy way to find the solution of a linear system really fast. Okay, I want to look real quick at just one of these, just so you, just so you've seen one of these. It's been a while since you've done one like this, but this is something that you'll see again and again at various levels. You'll see that it's useful to be able to set up some linear systems to solve real world problems. Linear systems apply to real world problems continuously. It happens again and again in science well, here's just an example. So how would we do this problem here? Just read through this real quick, and then I want you to kind of walk me through it. So what do you think? What are some, talk me through this, what are some things we want to consider when doing this problem? Deciding on an approach. Yeah, go ahead.
Put them both into equation.
Okay, you gotta put them both into an equation. To put them in an equation, we need to have some variables, right? What are the variables gonna be here?
One, total cost, that's miles driven.
Okay, total cost and miles driven, good. And what's one way in questions like this, what's kind of a hint that's always gonna direct you right to the variables, AKA the unknowns? Say it again? Well, okay, what the rates are might be a clue. A lot of times, just look at what's being asked for, right? The whole point of a word problem is to answer a question, and typically you're trying to find the value of an unknown. And so most times, it's gonna ask you directly. You're gonna ask for these two things, or it might only ask for one. But by knowing one, you can pretty much get the other. Those are going to be the unknowns. Because it's a linear equation, it's not as though you really have to have a dependent and an independent variable, but it's not a bad idea to think about it that way. Of the two, Elton, you chose the right one. Well, how come you chose X to be the number of miles and Y to be the cost?
The cost increases as
Okay, yeah, so typically we'd say Y is the dependent variable, right? X is the independent variable. And which one makes more sense? The number of miles driven depends on the cost, or the cost depends on the number of miles driven with the rental cars? Maybe the second one, right? The cost depends. So, technically we probably should let Y equal the cost. So those are our two variables, right? And let's define those. So X equals number of miles, Y equals cost. And then we've got to come up with equations for both situations, right? They're just giving us, we're comparing two rental companies. So let's color code these and say, Eagle Rent-A-Car charges a flat fee of $26.04 plus 15 cents a mile. How would I write that then as an equation, as a linear equation?
15 plus 26.
Okay, good. So we'd say for that car company, it'd be Y, which is the total cost, equals the amount that we're paying for the mileage rate, right, plus the fixed cost. And then if we compare that to Easy Rentals, there's no flat fee but 70 cents a mile, so Y equals Good, and we would just cross those lines, right? No big deal. Okay, we don't have to do that part. Okay, so next thing I want to show you, we're going to expand our talk of linear systems, and we're going to talk about, instead of just talking about 2x2 linear systems where we've got x's and y's, and you have a great understanding, you've done a ton of that stuff through this point in your algebra careers. We know, as we've already talked about, that the solution to a 2x2 linear system is going to be the places where those two lines cross. But what about a 3x3 linear system? And that might sound a little weird. How can you have a linear equation involving 3 variables? That's a little bit of a misnomer almost, right? It may seem that way. How can something like this, tell me why this equation, if A, B, C, and D are just real numbers, but x, y, and z are variables, how can that be linear?
It's a three-dimensional.
It's okay, and that's what the answer is going to be. The graph of this is going to be a plane, but why is it linear? We've always assumed linear meant line, right? And it's, well, it's straight, yeah. But that's really not the reason. Lines, I mean, yeah, linear means pertaining to a line, but a linear equation does not necessarily have to be a line. This isn't a line, but why is it linear? What does this share in common with what we've always known to be just the equation of a line? So this is what we call linear equation in standard form. Goes forever, sure, that's a possibility, yeah.
Its values and solutions for this equation has either a one-to-one correlation or a one-to-many correlation.
Okay, like a function, yeah. What do you notice about each term in this equation, though? There's a pattern there, because we could make this, here's another linear equation. Oops, I should have made that. That should have been a W. It's out of order. Oops. I better fix it. There's another linear equation. What do they have in common, Ruth? Oh, okay. Okay, so in each case, they can be written in a standard form, right? Where each variable is to what power? First power, and it's multiplied by a real number constant. As long as that pattern is true, you can have as many variables as you want, and it's still considered to be a linear equation, okay? So that's the pattern we're really looking at. So something like this is representative of a plane, right? And how is that the case? Well, we just add an extra dimension here, right? So we've really now got the x-axis, the y-axis, and coming out of the board is the z-axis, right? And so now we got a plane that's embedded in a 3-space. Yeah.
What would it be an example of a nonlinear system?
Well, something like this. Okay. I mean, there's an infinite number of examples, but there's one where I've got x is being squared, for example. Okay. Make sense? All right. So then, when we're looking for the solution to a 3x3 linear system, what do you suppose we're really dealing with here? Instead of where two lines intersect, we're talking about where what? How many planes? 3 planes intersect, exactly. And so there's a bunch of different ways that can happen. There's more possible ways that they can interact than just 2 lines, right? Now look at this first row up here. What can you tell me about? They're pretty different. But if we're looking for the places where all 3 planes intersect, right? Where points that are common to all 3 planes, how many are there in all those situations? None, right? None. So those would all be situations where in Moodle we have no solution kind of thing. Okay, what about something like that? single solution, right? There's only one point, and there it is, where those, and it could look different ways. I mean, maybe this plane is tilted sideways, and it's, it doesn't have to look quite that nice, but that's the kind they were usually looking for, as a single solution. What about something like that? Infinitely many. But what's interesting about this is when we say infinitely many here, we can say more than just infinitely many. We could even say, okay, what's the equation of that line where all three of those planes line up, right? I'm not going to go there right now. We'll come back later in the year, and I want to show you a way where you can do some constrained solutions. This is really well above the level of an Algebra 2 class, but you guys can handle this. So I'll show you this later on. And the calculator will tell you what the answer is. So you can actually see what the constraints are. So in this solution, you can see that it's going to relate the three variables, x and y and z, so that we're going to come up with the equation of one trajectory through three space. It's pretty cool, yeah.
So like with the planes up there, like would they be infinite like a line?
Yeah, they're all, right, you can't draw an infinite plane,
Yeah.
just like you can't draw a line, so we always just represent it by just a piece of the plane. Yeah, but they understand they really go forever, yeah. Okay, so now here's the cool part. This you gotta really follow this closely though, because there's a lot of moving parts to this. But here is the trick for solving systems like that. What kind of a system is this one?
Four-dimensional.
What is it?
Four-dimensional.
Four-dimensional, so we'd call it a 4x4, right? What are the variables? W, X, Y, Z. Okay, now this is a little bizarre one. Geometrically, what would that look like?
Yeah, exactly.
Well, it's pretty hard to imagine it, yeah. That's gonna be, what do you suppose, I mean, that one's a little bit strange, because now you're talking about a four-dimensional space, right? What's embedded in a four-dimensional space? Well, a volume. So you'd be looking at volumes embedded in four spaces intersecting, which we can't visualize because we only live in a three-dimensional universe. But there might be some other universes where this would make perfect sense. Say it again.
You know, if you go watch, okay, I don't know if this doesn't relate at all. But if you go to a movie where they do the smells and stuff, that's called 4D. What is
Yeah,
it?
like
Well,
the outside thing
that's-
in Disneyland.
That's called a marketing gimmick. Yeah.
So it's not really.
No.
They're lying.
Yeah, they lie to you, yeah. Okay, so here's how we do this. Now I have to introduce something to you. You guys have probably never heard of a matrix before, right?
No.
Have you, raise your hand if you've heard of a matrix in math before. Yesterday, okay. Okay, so a matrix in math, matrices, there's a class that you guys will hopefully all take. When you go on to college and you're doing your math stuff, whether you're a math major or just taking math on the side, which I'm assuming you're all gonna do, you're gonna take a class that's gonna be called something like linear algebra and matrix theory or something like that. It's a really valuable class. And it's, the thing about it now is a lot of the stuff that, like back in the day, that I had to learn to do manually on using matrix row operations and things, your calculators will do for you, which is really handy. But there still are there's some parts of this linear algebra that your calculator can't do also. And so it's really powerful stuff. Solving, I didn't even take an opportunity to solve a 3x3 system for you manually, because you just don't do that stuff very often. We can come back later. I don't want to waste any time this semester doing it, but we can talk about how you could take an arbitrarily big linear system and solve it algebraically. But it's hard. I mean, I wouldn't say it's hard. It's just tedious, and it takes a long time. If you wanted to solve like an 8 or 8x8 or 9x9 linear system, that would take you a long time to do. It'd take me a long time to do. And it would be, there's opportunities to make errors, right? But with a calculator, you can do it just like this. It makes it really, really simple. So all you have to do first of all is to be able to set up the matrix. So to set up the matrix, here's the way you have to do this. All the equations must be written in standard form, which they're all typically going to be anyway. These all are. That just means that the variables are all represented in the same order. So by convention, we just say alphabetically. And then the constant is always put on the other side of the equal sign, right? Does that make sense? Okay. And then if we do that, we can set up what's called there's really two parts to this. There's going to be the, in this case, the 4x4 coefficient matrix and the 4x1 constant matrix, but we're going to shove them all together into one big matrix that represents the whole thing. And all it is just the coefficients that are represented up there, the coefficients of the variables in the constant in the appropriate order, right? Because they're all written in standard form. So we enclose the matrix in square brackets, and let's just build this matrix row by row. So in order, in the order dictated by standard form, what are the coefficients of the first row? 1,
3,
let's see, yep, and then
6,
6. Okay, next.
3, 3, 3, 4.
Next row.
4, 0.
Okay. 0. How come?
Because there's no X.
Because there's no x. We have to include that though, right? We have to include all of the 5 coefficients in every row. So if there's a missing variable, it means it's a 0 coefficient. Okay, keep going.
5, 2,
Okay.
1, 3, 1, 4, and 6.
Okay, so that's the matrix I'm going to input. Let's see, I'm going to grab this.
Matrix, dude. Have you not seen that? Okay.
So did you think when I started mentioning the matrix, I was going to show you how to like stop time and move, do crazy things?
Can you do that?
Oh yeah, next semester I'll show you that stuff. Okay, so here's how you do this then, on your calculator. Okay, you go to the matrix screen, so second matrix, and that's what you see, right? There are 3 menus there. The first menu is the list of all the matrices that you can work with. At the same time, if you want to, we'll probably only use one at a time for now. The next menu, the math menu, is all the different things you can do with matrices. I mean, look at all these different row operations you can do. There's a ton of them. A lot of that's going to be, we're not going to do hardly any of that right now. But hopefully, I'd sure like to have an opportunity to do a little bit more of this at some point. Maybe it won't be this year, but at some point in the future, we'll all talk more about this stuff. And then edit. This is the one where we're always going to start. This is where we build the matrices. So we're going to build matrix A to match this matrix. Okay, so then we hit enter. First of all, we have to define the size of the matrix. Anybody tell me what the size of that's going to be?
5 by 5.
4 by 5. Right, it's always the number of rows by the number of columns, right? Okay, so this is going to be 4, enter 5, and then it builds the template, right? And now I just fill in the blanks. So conveniently, it goes in the order of rows from left to right, just like you're reading a book. So just 1, enter, -2, enter, etc.
Error.
Uh-oh, what'd I do?
You didn't click enter between 2.
Oh my goodness.
Can we just start all over?
No.
Okay.
Okay, there it is. Fine. Got the matrix. Now what? Okay, you have to quit, because if I just start to do stuff now, it's gonna assume that I'm trying to embed something within one cell of this matrix. I'm trying to embed something more complicated, like a matrix within a matrix, which we don't wanna do. So we're gonna quit, and then we're going to go down to the matrix screen again, and we go to math. Okay, now what we wanna do, this is a great trick too. I don't know, I think this is a pretty good one. There's a lot of ways that this is taught, but this is by far the best for some reasons that will become more evident to you as you use this later on. We want to go down this list quite a way, so I'm actually going to go up from the bottom. We want to go to number B. RREF. Now what that really stands for is reduced row echelon form. So what we want to do is we want to put this into the form of a solution. Okay, so we're going to choose B, and then we're just going to do reduced row echelon form to matrix A. So then we go second matrix A, close the parentheses. Okay, now I hit enter, and that's what it does. Okay, I want you to explain that to me. That's my solution. Why does that represent my solution?
1W = 4.
Ah, good, because if we go back and look at this matrix, remember what each of the columns represented. Each row represented an equation, but essentially this first column, these were all what?
W's.
Coefficients of W. These were the coefficients of X, coefficients of Y, coefficients of Z, and the constants, right? So what is that first row saying right there then?
W equals 4.
Yeah, 1 times W equals 4. 1 times X equals -5, etc. So then, as long as, so here's what you look for. You know you've got a singular solution, or you know you've got a unique solution if the first square part of the matrix looks like that. Looks like what we call the identity matrix, meaning it's got upper left to bottom right is a diagonal of only ones, and every other element of the matrix is a 0 of that square part, right? If I just ignore the last column. And then if that's the case, the last column is just giving me the values of the variables in order. Pretty cool, right? So then we would just enter this as that ordered quadruple. Yep.
Is it possible for that to not be the case?
Yes. Yeah, we'll look at an example. Okay. So there's one solution to this, and that's it. Okay. Oops. Oh, what did I do? Okay, so. Oops. So that was our solution, right? Okay. All right, so look at one more. Look at one like this guy right here, how about? So put that one in for me. I'll do the same thing. And you might have the question then, well, what do I do? I've already got a matrix. I don't know how to clear these things. There's probably a way to do it, but I've never bothered because you never need to. If I want to build a new matrix, I just build it over the top of the old one. So how big should this one be? I don't need to draw it out. I'll just put it directly into the calculator.
3 by 3.
3 by 4, good. So would this work for 2 by 2 systems also?
Why not?
Yeah, it would. If you want to. I mean, it seems like it's almost easier just to do the crossing the lines, but it works for 2 by 2 systems also. So where do I go? Second matrix, math, B. And I can even just skip and just go B like that, right? Alpha B, and it pops it in there for me. Okay, what's the deal there?
It's not.
That's not the same thing. Look what that's telling me. That's telling me that that first row is telling me that x plus 2z equals 0. Y minus 1.25z equals 0. And the last row is telling me what? Telling me 0 equals 1. Okay, yeah, that's telling me no solution, isn't it? So here's the way you can read this. If you look at this and you don't get the identity matrix for your first square part of the matrix, then you look at the bottom row. If the bottom row is telling you something that's untrue, it's an untrue statement, then we always interpret this to mean what? No solution, okay? Which this one is. Now the other kind that I'm not going to mess with for now would be, what if you had one just like this, but the bottom row were all zeros? Then it would be infinitely many, and these upper rows would be telling you the constraints on the system. Those would be telling you the equations of any lines, see what I'm saying, where there were overlaps, right? Okay. Most of the time, though, what we're really interested in is just the first kind, where there's a single solution. Okay. All right. So last one. Oh yeah, forgot something like this. Okay. So this is kind of a cool problem here. So what if we wanted to? We want to fit the exact quadratic function in general form to this system. First of all, what is a quadratic function in general form? Quadratic function in general form is just this. Ax squared plus bx plus c. So y equals ax squared plus bx plus c, right? We want to fit that. So how could we use the fact that we know these 3 points to find what, to fit that to the quadratic function, to find the exact quadratic function that goes through all 3? Say it again. Bottom on the. Oh yeah, just doing the fit. You're right. That's true. Yeah, there is a shortcut, but how can we do it without using? You're talking about regression. Yeah, yeah. How can we do it without using regression? Any ideas?
Plug in the numbers in the quadratic formula.
Not exactly. Here's how we could do it. Okay, real quick. If I know that this is the equation for the general form for a parabola, quadratic function, right? Each of these are solutions, correct? So for example, this tells me that when x equals -6, y equals 0, right? So look what I could do then. I could take this point and I could say, okay, well then I'm going to turn this around and put the y on that side instead. And then let's color code this. This point right here we're going to call red. So I'm going to get a times -6 squared plus b times -6 plus c equals 0. Right? Everybody see that? How about this point right here? Well, that's going to give me a. Oh, are we done? Oh my gosh. So disappointing.
So just
Do you?
so you just extrapolate the equation and solve it like